Hello, my name is Eric Rasmussen, and this is part one of my presentation project for solar and alternate energy systems. The title of the article that I reviewed is Life Cycle Energy and Climate Benefits of Energy Recovery from Wastes and Biomass Residues in the United States, and it was authored by Bo Liu and Deepak Rajagopal. The purpose of this paper was to determine the best way to convert any number of different bioenergy sources. Data was analyzed on 15 different types of conversion technologies and then used to determine the potential renewable energy production, net energy gain, and greenhouse gas emission reduction for each distinct type of waste. The goal was to find the conversion pathway that best maximizes renewable energy production, net energy gain, and greenhouse gas mitigation. It is found that the source of electricity consumed during processing and the environmental footprint of the displaced products are key in determining the best use of wastes and biomass residues. The utilization of all available wastes and residues in the United States can generate between 3.1 and 3.8 exajoules of renewable energy, but only around 2.4 to 3.2 exajoules is actually delivered. And between 103 and 178 metric tons of CO2 greenhouse gas emissions are displaced. For any given bioenergy source, no single conversion pathway simultaneously maximizes renewable energy production, net energy gain, and greenhouse gas mitigation. At the beginning of the new millennium, energy insecurity, global climate change, and stagnant rural economies led to policies supporting domestic biofuels as a renewable alternative fuel in more than 60 countries around the world. Because of this, global production of ethanol and biodiesel almost quadrupled from around 35 billion liters to around 135 billion liters in the span of 2005 to 2016. All of these policies had two major flaws. Using food crops for biofuels, mainly corn, sugarcane, soybeans, canola, and palm oils, were responsible for food price inflation, which also led to rising energy prices, adverse weather shocks, currency fluctuations, and trade policies that had negative effects on poorer households and developing countries. And secondly, growing these food crops for biofuels required a lot of land, water, nitrogen, and other farm chemicals, which meant low net environmental benefits. Biomass residues from agriculture, dairy, forestry, and household wastes are much better candidates for bioenergy. The United States Department of Energy estimates an annual availability of 233 million tons of dry waste. To put this in perspective, the approximately 60 billion liters of corn ethanol produced in the United States in 2017 required about 150 million tons of corn, assuming a yield of 402 liters of ethanol per million ton. Furthermore, wastes and biomass residues can be used to make different alternative energy products, including electricity along with heat, biomethane, ethanol, renewable diesel, or biojet fuel. Some of the challenges of sustainable bioenergy include the collection, transportation, and storage of biomass feedstocks that are costly and could account for over 50% of total cost in the supply chain. The consumption of wastes also varies from one place to another, and their processing requires substantial energy inputs. National scale policies tend to ignore local trade-offs, leading to suboptimal use of scarce resources. The majority of previous life cycle assessment studies have focused on either a smaller number of waste types, certain types of bioenergy product, or certain conversion technologies. Comparing the effectiveness and environmental impacts of all feasible conversion pathways for all types of waste from a systems perspective is necessary for policies that address the best use of waste and biomass residues. This study attempts to determine the net energy gain and the global warming potential of energy recovery from waste, which pathways simultaneously maximize renewable energy production, net energy gain, and climate benefits for each type of waste. This table describes the 15 different conversion pathways that are used in converting waste to energy. These figures show the energy, net energy, and emissions from waste biomass utilization in the United States. Here is a sensitivity analysis of emission estimates. This figure is the county level renewable energy production, net energy, and emissions. And this table is the total renewable energy production, net energy gain, and global warming potential across different scenarios. This table lists the synergies between renewable energy, net energy, and global warming potential at the county and state levels. Here are some of the calculations used in this paper to determine which pathway is best suitable. In conclusion, maximizing the benefits of waste conversion requires attention to the life cycle implications of different technology pathways, the spatial distribution of waste feedstocks, the local conditions under which waste feedstocks will be processed. The policy insight that emerges from this analysis is that national mandates such as the U.S. Renewable Fuel Standard might not maximize even renewable energy production, let alone environmental benefits. Renewable portfolio standards, which is a widely employed policy in the electricity sector, could lead to suboptimal use of waste biomass. From a methodological perspective, this analysis illustrates the value of combining LCA with spatial analytic techniques for multi-criterion assessment of alternative conversion pathways and the identification of hotspots for the refinement of existing energy policies. Indexing volumetric targets and mandates, as well as financial subsidies for renewable energy to life cycle emission-based performance measures will lead to more sustainable use of wastes and biomass residues. This study is a first step towards using a common system boundary for a consistent comparison for a large variety of waste conversion technologies from the twin perspectives of net energy gain and climate benefits. Incorporating non-greenhouse gas environmental considerations, including air quality impacts and fresh water use and water quality impacts, as well as an assessment of the levelized life cycle cost of energy for the different pathways, are two important directions for future research. And all of the material in this presentation was from Life Cycle Energy and Climate Benefits of Energy Recovery from Wastes and Biomass Residues in the United States. Hello, my name is Eric Rasmussen, and this is part 2 of the presentation project for ET415 Solar and Alternate Energy Systems. and this is on landfill gas collection and processing systems. Landfill gas is a natural byproduct of the decomposition of organic material in landfills. LFG is composed of roughly 50% methane, 50% carbon dioxide, and a small amount of non-methane organic compounds. Municipal solid waste landfills are the third largest source of human-related methane emissions in the United States, accounting for approximately 14.5% of these emissions in 2020. The methane emissions from municipal solid waste landfills in 2020 were equivalent to the greenhouse gas emissions from about 20.3 million passenger vehicles driven for 1 year, or the CO2 emissions from nearly 11.9 million homes' energy use for 1 year. This being said, failing to harness methane emissions from MSW landfills is a lost opportunity to use a significant energy resource. When MSW is first deposited in a landfill, it undergoes an aerobic decomposition stage. There is very little methane generated during this phase. Within 1 year, anaerobic conditions are established and methane-producing bacteria begin to decompose the waste and generate methane. This diagram illustrates the changes in typical landfill gas composition after waste placement. Bacteria decompose landfill waste in 4 phases. The composition of the gas changes with each phase. It is also possible for the waste to undergo several phases of decomposition at once. Instead of escaping into the air, landfill gas can be captured, converted, and used as a renewable energy resource. Using LFG helps to reduce odors and other hazards associated with LFG emissions and prevents methane from being released into the atmosphere and contributing to local smog and global climate change. LFG energy projects generate revenue and create jobs in the community and beyond. This graphic illustrates the collection and processing of LFG to produce methane for multiple uses. LFG is collected through vertical and horizontal piping buried in an MSW landfill. The LFG is then processed and treated for use. Some uses of LFG include industrial and institutional uses, arts and crafts, pipeline gas, and vehicle fuel. This graphic shows 3 stages of LFG treatment. Primary treatment removes moisture as the gas passes through a knockout pot, filter, and blower. Secondary treatment involves the use of a cooler and other additional moisture removal, followed by silazane, sulfur removal, and compression. After the impurities are removed in the secondary treatment stage, the LFG can be used to generate electricity or as a medium BTU fuel for arts and crafts or boilers. Advanced treatment removes additional impurities and compresses the LFG into a high BTU gas that can be used for vehicle fuel or injected into a gas pipeline. Waste or tail gas is sent into a flare or thermal oxidizer. There are 2 types of landfill gas collection systems. There's passive collection, which collects gas simply by inserting vents into the landfill and allowing the gas to flow up through the vents. These vents may be vertical or horizontal and may extend lengths up to 75% of the depth of the landfill waste. In order for a passive system to be effective, the landfill must have adequate internal pressure to push air upwards. Secondly, there is active collection. An active collection system creates a vacuum inside extraction wells in order to extract the landfill gas. The vacuum is generated by using blowers. The extraction wells are connected to a larger collection pipe. Extraction wells can be installed vertically or horizontally within the landfill. Here we have a schematic of a passive collection system. The efficiency of landfill gas collection is the amount of LFG that is collected relative to the amount generated in the landfill, and it is dependent on a number of factors. Among the factors are horizontal versus vertical extraction wells. Horizontal and vertical collectors have different levels of efficiency. Horizontal extraction wells are more often used while the landfill is still active and waste is still being added. Vertical collectors are usually installed after the system is closed and waste is no longer being added. Vertical systems are more efficient than horizontal systems because a stronger vacuum is created by the closed system. Decay speed is also a factor. Waste decay that occurs before landfill gas collection systems are in use will subtract from the overall collection efficiency. Because the LFG that is generated is not collected, the decay speed largely depends on the type of waste deposited in the landfill. And organic waste will decay faster than non-organic waste. The type of cover used in the landfill can also contribute to the efficiency. Materials used for daily covers include wood chips, foams, or plastics. The site's native soils are generally used for intermediate covers, and the final cover is regulated much more specifically to give a higher efficiency. Also, the design of the collection system. The layout and design of the collection system will affect the overall efficiency of LFG collection. Calculations are performed to determine design parameters of an LFG collection system. These calculations will be used to determine the spacing of extraction wells, the size of blowers, in the case of an active system, and other specifications. Landfill gas that is not released to the atmosphere can be flared or used for energy through a variety of processes. Flaring is the combustion of landfill gas that is collected. It can occur in open air or in an enclosed container. Flaring is used to burn landfill gas in order to convert methane to carbon dioxide. Enclosed flaring is more expensive but has better efficiency. Flaring does not result in utilization of landfill gas or production of energy. Flaring is a method of disposing of LFG and is used to reduce the greenhouse gas contribution of landfills. Here is a typical setup for a flare system for landfill gas. Utilization of landfill gas, direct use. Direct use is the easiest and cheapest way to use recovered LFG. The LFG is sold as a medium BTU substitute or supplement for natural gas. Electricity generation. Electricity generation is the most common usage of collected landfill gas, making up approximately 70% of landfill energy projects in the US. There are multiple technologies available for the conversion of LFG to electric power, including combustion, gas turbines, and internal combustion engines. Here's a flowchart of a basic LFG collection and processing system. It starts with landfill with the waste in place, landfill gas, extraction wells and piping, then flows to primary processing of landfill gas and flare. Then there is additional treatment of landfill gas, and finally, landfill gas energy project. The references I used for this presentation are basic information about landfill gas, which was published by the Environmental Protection Agency, and also landfill gas generation and collection, which was written by L. Hayes and H. Yoon. Thank you.